What we want to look at today is just kind of another variation on the permutations, and that is, what do we do if some of the things that we are arranging are identical? Okay? In the example we just looked at, where we were looking at with the 8 horses, those 8 horses are all distinct. They're all different horses. Okay? But we could consider a situation where we're not really concerned with the horses themselves, but the owners of those horses. Okay? And let's say that one person owned 3 of the 8 horses. Okay? Well, if we're just looking at how the owners did, or you could say the trainers even, or something like that, then you would have some repeated items. Even though they're just different horses, it's the same owner, the same trainer. So if that's what we're focusing on, we're not going to get a distinct or a different permutation. Okay? So, another example of this would be, for example, let's say we were arranging letters of this word trigonometry. Okay? Now, when we're talking about permutations, the order matters, but if I were to just switch this T and this T, would that technically be a different permutation? It would. Would it look any different?
No.
No. Okay. So what we're talking about today really are what are called distinguishable permutations. If something is distinguishable from another, it means we can tell a difference by looking at it. Okay. So if I were to just switch those T's, it's going to look the same, so that would not be another distinguishable permutation. Okay? Same thing if I switched these O's, or I switched the R's. Okay? So the question is, how do we figure out how many distinguishable permutations there are? Alright? Well, let's look at a basic rule and then apply it. Okay? We don't want to include these repeated permutations. So here's what we'll do. Okay? We have a set of n objects, and there's n1 of one kind of object, n2 of another kind, n3 of a third kind, and so on. In other words, we have these different kind of sets of objects. In this case, we have letters. Okay? And to kind of explain what this is talking about, we could say, okay, there are 2 T's, there are 2 R's, there's only 1 I, there's 1 G, there are 2 O's, there's 1 N, we already have the O, so there's 1 M, 1 E, and 1 Y. We already have the T and the R accounted for. Okay? So this is what this first part of this rule is talking about. We have these things that we're arranging, but there's a different number of identical ones. Okay? So how are we going to handle this? The number of distinguishable permutations of the n objects is given by n factorial over n1 factorial times n2 factorial times n3 factorial, and so on. Okay? Now I have a little note there we'll look at in a moment. But here's how we would do this. Okay? There are 12 letters total. So we're going to start by putting 12 factorial. Then we're going to divide by 2 factorial times 2 factorial times 1 factorial. But what's 1 factorial? 1. And then another 1 factorial. Then we have another 2 factorial. And then we have 4 more 1 factorials. Okay? I don't bother writing down the 1 factorials. Okay? But anything that you have more than 1 of, you need to put that with a factorial in the denominator. And what that will do is eliminate all of the cases where we just switch the T's, or we just switch the O's, or just switch the R's. Okay? Does that make sense?
What goes in the numerator?
The numerator is n factorial. There are 12 letters here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
So you put factorial 12 in the numerator.
Yes, because we're arranging all the letters. And here's the thing. If we were not arranging all the letters, that would be a very complex problem. Okay? So, for these ones, we're going to be arranging all the letters. So, we have 12 factorial over 2 factorial times 2 factorial times 2 factorial. Did anyone actually try that? It's going to be a big number. Five, 9, 8, 7.
5, 2, 0, 0.
All right. So there's almost 60 million different arrangements, distinguishable arrangements of the word trigonometry. Okay? So that's a lot. By the way, just from this, you can kind of see, like with computer security and things with passwords. Okay? Even if we only had 12 letters, even if some repeat, there are still millions of possibilities. Okay? And the fact of the matter is, the more letters you have or numbers that you have in your password, the security level kind of grows exponentially. Okay, even if you just use the letters, okay, a 4-letter password is 26 times more secure than, or there are 26 times as many possibilities as a 3-letter password. Okay, and that's ignoring uppercase versus lowercase. And that's ignoring numbers or other symbols. Okay? So, you can see here how many different possibilities come when we have 12 digits. So that's why a lot of passwords, they'll make you use at least 6 digits. They'll make you use a number. They'll make you use at least one symbol or something. All that is just to increase the level of complexity and make this number bigger, basically. Okay? So, because if you have a 6-digit passcode and and all those digits could be lowercase, uppercase, a number, or one of the special characters, which I'm not sure how many special characters there are. So there's 10, 11, 12, 13, 14, 16, 18, 20, 22, 24, 26, 28, 30. There's 30 special characters, at least on the keyboard. Okay. You would have 52, 62, 82. For a 6-digit passcode, you'd have 82 to the 6th power possibilities, which is really big. Okay? So, if someone's going to break your password, unless you use like a word out of the dictionary, they're going to have to run through potentially that many possible passwords before they're just going to be able to guess it. So, but they do have password cracking software that does it, and it'll run it for as long as it needs to until it finds it. All right, let's take a look at one other example. Just try one here. Any of you follow baseball at all? A few of you? Okay. So baseball team, when a coach or a manager is setting up his batting lineup, one thing they pay attention to is whether the batters bat left-handed or right-handed. Okay. So let's say that we have 9 people in the batting order, like we normally do. 5 of them are left-handed, and 4 of them are right-handed. Okay. How many different permutations can we have if we're just considering whether the batters are left-handed or right-handed? Okay. How would we set this up? Someone want to tell us? Or take a shot at it? Is that a hand, Rachel, or?
No, but would it be 9 factorial over 5 factorial and 4 factorial?
That's exactly right, okay. 9 factorial would be all 9 people, distinctly. And then you have 5 left-handers, and you have 4 right-handers, okay? So that would be how many different lineups they could come up with. If you think about it, and this will simplify some of these problems, really what you're arranging, you could think of this as arranging 5 L's and 4 R's. There's one permutation right there. Okay, just like we had the word trigonometry, we could make this 5 L's and 4 R's, and we're just rearranging those letters. Okay? So we do that, and
126.
what'd you get?
126.
126?
Yeah.
Okay. So the manager has 126 different possibilities, just looking at what hand the batter's batting on, what side of the plate they're batting on. Okay? Does this make sense how we set this up? Any questions so far? All right. Before we go a little bit further, let's do a quick review with combinations, okay? We've done permutations. I don't want us to forget about combinations, all right? Let's take a look at a possible type of problem. We said that you're going to be dealing with cards throughout just because they're really useful for probability, okay? So let's say we had this case. A standard poker hand consists of 5 cards dealt from the deck of 52. How many different poker hands are possible? Now, one thing, you won't necessarily always be given this in parentheses, but notice this. We're talking about a hand of cards, right? Or a group of cards. The person who's holding them can put them in whatever order he wants once he gets those, right? So in this case, we're not dealing with a permutation. It would be a combination, all right? So what would be the combination that we're evaluating? Zach?
It would be like 52 factorial over 52 minus 5 factorial 5. That's 5 factorial.
And then 5 factorial? That's correct, okay. That would be the combination plugged into the formula. This is 52 choose 5. Okay, there's 52 cards to choose from. We're picking out 5 of them. Okay, so that's what we've got. All right, go ahead and evaluate that. You're going to have to be able to do this tomorrow anyways. You can use your calculator, but make sure you all can evaluate the combinations. one? Okay. What? Oh, tonight you're gonna- okay. If you go into math and scroll over to probability, and actually that's where permutation combination is as well. Yeah, you can actually, if you do that and hit enter, you have 52, that, and then you put the 5 after. Yeah. Alright, so what did we get?
2,598,960.
916?
960.
960. Thank you. Okay. Alright, so a whole lot. 2,598,960 different sets of 5 cards that you could get. Okay? Is anyone not getting that? I want to make sure everyone has that before tomorrow. You can find those. Okay, I want to just introduce an idea here with these combinations. And we're, like I said, we're just going to be able to introduce it. We'll talk about it more on Friday. But when we have multiple events, okay, we have multiple events. Here it says we're forming a 12-member swim team for 10 girls and 15 boys. The team must consist of 5 girls and 7 boys, okay? How many different 12-member teams are possible? Here we have one of our counting principles, and like I said, we'll talk about this more on Friday. But we have 2 different events, and our fundamental counting principle says that if there are a certain number of ways to do one event, and there's a certain number of ways to do another event, then how do we figure out how many ways there are to do them together? Yeah, we multiply those together, okay? Now, notice we're talking about events that are independent of each other. In this case, what girls you pick is not going to impact what boys you pick, okay? So, how would we pick, or how many combinations of girls could we get? Very good. We have 10 girls to choose from. And we're going to choose any 5 of them. Okay? But then we have to pick the number of boys. Okay? How would we pick, or how many combinations of boys are we going to have? 15 choose 7. Okay? Now, for every one of these combinations of girls, we have this many combinations of boys, right? So there's where our counting principle comes in, and we would multiply those together. That is going to give us how many different teams we could come up with. And notice here, order doesn't matter. We're just creating teams, all right? But that's how many different teams we could come up with. Okay? And our answer would be
1,621,620.
Alright? Okay? So, we have a lot of options. Okay, different combinations of people that we could put on this team. Alright? So, we'll talk about that. We'll pick it up from there a little bit on Friday, and we're also going to actually get into doing probabilities on Friday. Okay? And that'll be it for today. So.